two presentations and a Q&A session towards the end. We've trying to split this up into 20-minute blocks. I appreciate the time is quite tight, just having an hour, so we will go through as quickly as we can. I'm quite happy for people to put questions into the Q&A session on the WebEx, and then when we come to the Q&A session towards the end, as session chair, I will go through as many of the questions as I can in the time available, and we will get our panel of experts to answer them. The questions that we cannot answer or just do not have the time to answer, we will make sure we respond to individual questionees following this webinar. So without further ado, let me please introduce our first speaker, which is David Hardacre, and his talk is on the guidance for additive manufacturing certification. Thank you.
Thank you very much, Carl. Good afternoon and good morning to everybody who's joined the call. Thank you very much for joining this webinar. My name is David Hardacre. I work for Lloyd's Register. I'm a lead specialist with Lloyd's. A little bit of my background is on screen at the moment, which I won't dwell on because we've got quite a lot to cover. But one thing I would just draw attention to is I'm a contributing member of many or various standards committees, and if anyone listening today is interested in joining or being a part of that, then you'd be very, very welcome. We certainly need any willing volunteers to help us to write the rules and get these standards published. But I'll be talking about that a little bit later anyway. So straight into the guidance notes. So we've recently, LR and TWI first published our guidance notes for the certification of additively manufactured metallic parts back in January 2016. It was updated in March 2017, and then very recently, April 2020, updated again. And it's the updated version that I'd like to take you through briefly this afternoon, and then Carl will be talking about how that applied to the actual certification, well, qualification of the TWI facility. So very basically, at a very high level, in order to certify a part, which would have a known application, a prerequisite of that is certifying the material. And so in conventional manufacturing, if you were to purchase bar or forging or plate, then that material comes with a material certificate. But with additive manufacturing, the part manufacturer is also the material provider. And so they need to satisfy both sets of requirements. So we need to certify the material as well as certifying the part. And just like other material production methods, a prerequisite of certifying that material is qualifying the facility that produces it. And so very basically, the fundamental foundation stones of certifying that facility consist of design, the feedstock, and the build plan. So the design, the 3D CAD model that inputs to the process, the feedstock, be it powder or wire for metallics, and the build plan, which would cover everything else. So all of the build parameters, paths, etc. We'll talk about that in a moment. So in order to certify a part, by the end of the process, we're basically compiling two sets of documentation. Which is how we worked it with TWI through their facility qualification. So on one hand, you've got the manufacturing plan. So this contains everything that is specific to what is being manufactured, specific to the part and the material, almost regardless of the facility. And on the other side, we have the facility procedures. So this covers how it's being manufactured. So things that would be typically the same every time, but aren't specific to the part that's being made. So whatever you're making, those procedures and work instructions typically remain constant. When we're looking at the facility procedures and qualification, as well as the manufacturing plan, we can basically think about 5 functional areas. So we've got design, materials, manufacture, post-process, and inspection. And within each of those functional stages, it subdivides into three categories. So people, so who's involved in the activities, what's the competency of those people, and how do we demonstrate that, the process itself that's being followed, and the product. So that's the output from each stage. And also, of course, these stages are interlinked. They don't occur in isolation. So when you're designing, for example, obviously there's a consideration of all of the other areas. So you're designing for manufacture in terms of buildability. You're designing for post-process. Certainly, if you've got complex internal structures that you need to finish the internal surfaces of, and certainly you're designing for inspection as well. So looking at, so stepping through the guidance notes in terms of an overview, we start off at the design section, and primarily we start off with a requirements capture. So this is capturing all of the design inputs. So typically a manufacturer will start off with a design concept. It might be a similar design. It might be something they've produced before using conventional manufacturing techniques that they now want to produce using additive for one or more reasons. But then you would take that design concept, and first of all, you would look at the regulatory requirements. So what are the legal requirements for this part? So I think here I've taken the example of a valve. So certainly if you were producing a valve in Europe, the legal requirements would be the Pressure Equipment Directive. There may be some application-specific standards, so a valve standard. The customer may have their own particular requirements, maybe in terms of pressure drop across that valve or discharge coefficient perhaps. And then when it comes to additive manufacturing, there will be some AM-specific standards as well, because unfortunately the valve standard doesn't contain anything about additive manufacturing yet. So the AM-specific requirements would hopefully be captured within AM-specific standards, but I'll come to that in a moment. So at this point, you've collected your design inputs, you've got all your requirements, and it becomes a case of, okay, how do we demonstrate that we're satisfying or complying with all of those requirements? So let me, there we go. I think it's missing a slide there actually. So when you've got all of those design inputs, your part geometry, the manufacturer would develop the part geometry to meet the design inputs, and also select a material specification. Just move on the slide. So the application-specific standards, so for example, if we're talking about a valve, unfortunately there's nothing in there about additive at the moment. So there are some of the requirements, but not all of the requirements. In an ideal world, it would cover additive and everything would be developed in compliance with that standard. So we need to fill those gaps. And the best way of filling those gaps would be to use some AM-specific standards. Now, I'm going to talk about this a little bit later, but unfortunately, not all of those standards are available either. So we still have some gaps remaining. And we fill those remaining gaps through a technology qualification approach. So that is used where there's neither industry-specific nor AM standards available. And it's about demonstrating an equivalent level of safety. So filling in those requirements gaps to demonstrate that equivalent level of safety, which may include additional testing or inspection. This is the slide that I was thinking of. So once you've collected all of your design inputs from those various sources, the manufacturer defines the part geometry. So if it's a like for like compared to the conventional, then fine. You would take the same probably design by rule approach that you've taken before. But if you want to get the best out of additive manufacturing, then typically you're designing for the method that you're using. So it's at this stage that a manufacturer might employ some topology optimization, either for lightweighting or for some performance enhancement. If they were to do that, then the design by rule option basically disappears because you start to get very complex geometries. But the manufacturer is then forced down the design by analysis route, which typically involves something like finite element analysis. In parallel with the part, of course, is the material. So those two things go hand in hand, part geometry and material specification. And I need to be clear here that this is the formed material. This isn't the powder or wire feedstock that's going into the process. This is the formed material. So it's at the design stage that the manufacturer will specify that, and this is where you'll get the acceptance criteria that we'll test against later on. But the designer will also specify the delivery condition of the material, so that includes specifying any thermal treatments at the post-processing stage. And then moving on from those, the manufacturer will develop an inspection and test plan. So how they plan to inspect it, how they plan to test the material, because of course before you start the process you don't have the mechanical or metallurgical properties. So those need to be established after the build in order to demonstrate compliance with the material spec and any standards or regulations that apply. And then, of course, there is the build layout, which includes not just the part, but any test specimens, qualification test coupons, support structures, etc. And the number and location and orientation of specimens is part of the process. Determining how many specimens you need very much relates to the part geometry in terms of the number of different features in there, certainly in terms of changes in wall thickness or different types of feature that need to be represented, because the specimens, in order to be representative of that part that they're going to be used to demonstrate compliance with the spec against, we need to understand that we've mitigated the risks not just of variability of properties throughout the part, but also potential variability throughout the build space. And I'll mention that a little bit later as well. So moving on to the material stage, so we've from the design stage we've got our requirements capture, we've got our form material specification. The manufacturer also has their equipment, of course, and we'll come on to that in the manufacturing stage. But typically they would then use, from this formed material spec, they haven't made anything yet. It's important from the design stage to get buy-in from an inspection authority. If you need third-party certification, it's very important to get buy-in from your certification authority before progressing to manufacture, because you do not want to find out later that that your certification authority wanted more specimens or different types of specimen or different sizes. That all needs to be assessed beforehand, so that there are no surprises or rebuilds later on. But from that form material spec, the manufacturer can now specify their feedstock spec. Now, when it comes to powder, certainly if there's any recycling of that feedstock, then there may actually be two specifications here. There may be a use specification and a purchase specification. If it's always virgin, or if it's wire, if there's no recycling going on, maybe it's a DDLB process, then they're often the same. But if the feedstock is being reused, then typically those would be different, because you wouldn't want to order against the same spec that you are using it against, because if you order powder that is only just within the limits of that specification, then the first time you recycle it, it may well go out of spec, and then you've got potentially a lot of wasted powder. So you would tend to develop a tighter spec for purchasing against. When we talk about material specs, many of you on the call will probably be familiar with these powder specs released by ASTM. So the top three are generic ones. Down below that are material grade specific that have been developed from these generic ones up at the top. There are more being developed, but this is what we have at the moment, and these are all powders, of course. When it comes to wire, typically if you're using a one process, so many manufacturers would purchase wire against a typical welding consumable spec, although many are now sort of going down a more bespoke route, tightening up those specs again and ordering wires that are specific to their process. But it very much depends upon the equipment setup that you have. When it comes to these feedstock specs, these ASTMs, it is just the starting point. So they're very good in that they contain references to other standards and specs for different test methods. They have chemical composition requirements, for example, minimum mechanical property requirements at ambient temperature, and they also contain some guidance for various thermal treatments as well. What they do not include are other powder requirements, so like regarding powder size and shape and size distribution. They don't have any guidance for reuse of powders, and they don't have any elevated temperature mechanical property data or other properties, so like fatigue or creep or corrosion, etc. So they're not complete. They're a good starting point, but the manufacturer would need to develop those to make them fit to what they actually need for their application. The specs are machine agnostic, which means they're not targeted at any particular powder bed fusion machine. The manufacturer is responsible for the feedstock purchase spec, which would be based on those, and it's good practice for a manufacturer to record and compare properties for each batch, keep a log, and then they can learn from experience in terms of what works in order to either tighten or relax their purchase specs a little bit. So when it comes to procurement and delivery of the feedstock, so that tends to come with, so the powder, for example, would be delivered with a material safety data sheet and a fairly basic certificate, which basically contains maybe chemical composition, powder size distribution, and perhaps not much more than that. So as part of in order to certify the formed part, it would be a requirement to do some further testing of that feedstock and do some characterization. And the manufacturer, certainly TWI in the case for their facility qualification, had to perform some independent powder testing at an independent lab and produced certificates that looked like this. This is a generic one. But this is the sort of, in terms of a powder characterization, this is the sort of information that's captured. So we've got, how it's sampled, which method was used, particle size distribution, again, which method was used, and there's some convenient references to either ASTM or ISO standards. These are just examples of methods. You might use light scattering, for example, in which case you would customize this certificate to your needs. Chemical composition is fairly self-explanatory, but what would be measured there would be compared against the spec, of course. Characteristic densities, so apparent density as a minimum, apparent and tap density is pretty common. Some manufacturers will use those to develop other indexes, so like the Hausner ratio, for example, or CAR index perhaps. And again, that becomes part of the learning in terms of their register, in terms of what they know works for their particular equipment setup. There we go. So moving on to the manufacturing section. So once again, we've got these inputs from our design stage. So we've got our geometry, we've got our feedstock spec that we're going to use for the qualification. When it comes to qualifying the actual equipment and processes within the facility, you basically follow a three-step, so what we call IQ, OQ, PQ. So IQ is installation qualification, OQ is operational qualification, and PQ is part or product qualification. So IQ, the installation of the equipment, that tends to have two steps to it really. So there's the equipment manufacturer themselves who will perform a factory acceptance test of that equipment, and then when it's installed they will do a commissioning activity or a site acceptance test, and the training of operators is usually occurs there as well. There may also be some auxiliary equipment, so things like lifts, sieving stations, that sort of thing. Moving on to the operational qualification, so the OQ stage. So the quality management system is just the very first step. So certainly as part of the AM facility qualification at TWI, they already had a QMS, an ISO 9001 certified QMS system in place, which we would expect to see as sort of a prerequisite, really. It doesn't mean to say that we wouldn't be able to continue with an AM facility qualification, but that tends to be the first step, just to make sure that those sorts of systems are in place in terms of revision and quality control. But there's nothing in those that is AM specific at the moment. So when it came to the AM specific aspects, looking at the departmental procedures in terms of what the activities are, who performs those activities and when they're performed, and then a level below that, TWI developed various work instructions with very detailed instruction on how each activity was performed. So that could be something like a pre-build checklist, for example, in terms of making sure you've selected the right substrate, how that's installed into the machine, fasteners correctly torqued, or if it's WAM, clamps providing the necessary restraint, etc. So very step-by-step instructions, which quite often lead to different records being generated, which all need to be stored either as part of the facility procedures or within the manufacturing plan if they are specific to that part. So, for example, in the substrate example that I just mentioned, the selection of the substrate, that, especially if it was to become an integrated within the final part, would be part of the manufacturing plan. Development of build parameter sets and either using standard sets from the equipment provider or optimizing and developing your own as a manufacturer would lead to, they would then be fixed and used for your qualification build. So that needs to be defined by the manufacturer in terms of the actual geometry in there, and that will be specific to the types and range of features within the parts that the manufacturer expects to be making. So, for example, if you've got, if you know that your parts are going to have a wall thickness between X and Y, then you would you would include test specimens within that qualification build that covered that range of wall thicknesses, and you would qualify those parameter sets for that range of geometries. And then establishing and then performing the testing and establishing consistency throughout that build space from those test pieces. Usually the target is to demonstrate with 95% confidence that 99% of the material is within the limits of the material spec. That would be the typical criteria, as well as establishing, of course, that the material properties meet the minimum that is stated on the material spec as well. So things like minimum tensile, yield, elongation, etc. And then after the OQ stage, where you've basically built qualification builds but not actually made any part, the manufacturer would then be ready to actually produce the first part. And a first article inspection will be required for the first off, and then obviously as you progress to making further parts within that batch, there would be a much smaller test regime, just a few specimens, just to demonstrate on a sampling basis that the manufacturer remains within the parameters of the range of their qualification. When it comes to post-processing, again in section 8 of the guides notes, you don't have to do thermal treatments first. You can separate parts from the substrate and then perform thermal treatments, but it's far more typical to do the thermal treatments first with everything attached, because one of the objectives is really to take care of the residual stresses that build up. But again, it depends upon your process. If you're using a powder bed fusion with electron beam, for example, then that may not be such a big problem. But again, it will be down to the manufacturer. It doesn't specify, the manufacturer can work either way, provided that the requirements are demonstrated through the inspection and testing. But the point here is that removal from the build space, there'll be a procedure for that in terms of the post-build checks, as well as the build monitoring as well, of course, and that's witnessed during the facility audit. Achieving the required delivery condition, so there might be a customized heat treatment or HIP stage, depending upon the process used. or it may be a customized heat treatment as well, because standard heat treatments may not be the best for additively manufactured parts. And then at this stage here, at this point, this should be the end of the property changing processes. So any mechanical finishing at this point would be about achieving the geometrical requirements, so getting the right finish, the right geometry, but shouldn't be really changing the metallurgy of the material that's been produced. One point to say here, though, is that any post-processing that is intended to take place on the part also needs to take place on the test specimens in order for them to be representative. So then moving on to inspection. Again, this is a fairly typical in terms of the ITP, so the inspection and test plan would have mechanical testing requirements, metallurgical test requirements, and non-destructive examination requirements. And then depending whether those criteria are met, it would be either a conforming item, in which case it's produce your documentation that leads to certification, or it would be a non-conforming item, at which point you need to get your customer involved on whether they would accept that as a deviation or corrective action, etc. So in terms of inspection, two routes: direct inspection or process qualification route. So what I described before with the build qualification is the process qualification route. If you're making fewer, maybe a one-off part or smaller volume production, then you manufacturer can go down the direct inspection route, where part is produced alongside multiple test specimens. We're short of time, so I'm not going to dwell on that. But if there are any questions, please put them in the Q&A. And then when it comes to final certification, so the first time, TWI, along with any manufacturer, would go through the whole process. But the next time they come to build a part, it's already a certified facility, and so you wouldn't go through all of that audit again, unless something had changed, of course, unless that facility audit was to be extended in scope, maybe adding a new machine or something. But typically you wouldn't repeat facility audits just for the sake of it. If it was producing a different part on the same equipment using the same procedures, etc. And similarly, if you were going to a new facility but producing the same design, then there wouldn't be the need to revisit all of the design assessment either, because that's already, there's no value in repeating that exercise when it's been done once. One caveat down here, though, is that witnessing of material testing is a prerequisite for any part certification. With conventional manufacturing, material has to be certified before you can certify the part. AM does not provide a loophole around that. I said that I would mention standards. I'm running very short of time. I'm sorry for rushing through, but these will be made available afterwards. I'm not planning on going through these in a lot of detail, but that's the sort of landscape of this ISO ASTM standards committees, which is split up into different joint groups looking at very specific items. These are the standards that are being produced at the moment. The takeaway from this is that the purple ones are the published ones. So if you remember that jigsaw puzzle that I showed you before, where we still have some missing pieces, well, all the blue ones here are those missing pieces. The turquoise or cyan-looking ones, they're draft. They're available as drafts. So if you have access through your national committees, then you've probably got access to those standards. But the purple ones are published. And finally, what I'd like to mention, when we look at the requirements capture and we look at that standards landscape and we try to, within that capture exercise, we're filling in those gaps, this is an example of how that might look. So at the start, you're preparing a route card. So there's some requirements in ISO ASTM 52904. Procuring the powder. Obviously, the design, each of these shaded sections here is a different role. So here's the design engineer who's selected the material spec, maybe performing a design for AM exercise, classifying the part. When it comes to the equipment itself, the equipment provider is providing that equipment, 52941 perhaps, performing their factory acceptance test. They do a site acceptance test, Manufacturer goes through that OQ stage, goes through the PQ stage, at which point they're ready to produce their first part, where we've got all this process control. There might be a recycling loop for the powder-based systems. Thermal post-processing, so HIP and other heat treatments, any other post-processors, non-destructive testing. Here's your test specimens coming down this loop here with your destructive testing and evaluation of those results, and then final inspection of the part. So that's a map of how it might look for powder bed fusion, and you can see that a lot of these numbers here are filled in, even though not all of those standards are actually published yet. The same process for direct energy deposition, some missing numbers, and same for DD-ARC, probably even more missing numbers in there. One thing that I would like to highlight though is running right through all of this, you've got ISO ASTM 52920, which is the standard for conformity assessment of AM facilities. It's not published yet, but it's on a fast track to publication. And down here at the bottom, we've got the qualification of the different roles involved at the manufacturer. So we've got an AM coordinator here, 52935, you've got a designer, and you've got the equipment operator as well. And no doubt more of those will be developed in the future. Okay, I've probably gone over my time, so at this point I'd like to hand you over to Carl, who will tell you a bit more about the implementation of all of this at TWI.
Okay, thank you, David. Could you pass me the ball?
Yep, you should have that now.
Okay, and I believe Stacey's going to swap the presentation over. Or do I need to carry on now? So I'll just wait for the presentations to be swapped. Stacey, are you swapping the presentations over?
Hi Carl, I have swapped them. Are they not showing up for you?
No, I'm just seeing David still. So I can just see the last slide of David. I don't know if anyone else is the same.
Yeah. Do you want to share your presentation then?
Right.
Can you see it now, Carl? Have you? At the top of my window, there's a little drop-down box where I can select to see different presentations.
Right, there we go. Sorry. Seems to be halfway through. Let's start again. There we go. Okay, apologies for some lack of IT skill there. So thank you, David. My name is Carl Hauser. I'm the section manager for laser additive manufacturing, coatings and repair within TWI, and I just want to now follow on David's presentation and just spend a few minutes, that's all I have, just going through some of the practicalities of what David's spoken about in order to achieve facility accreditation. So let's kind of start at the end of the story, really, I guess. So the image that you see on the slide is TWI's laser powder bed fusion facility. We have several machines in there, and it is now the UK's first accredited by Lloyd's Register powder bed facility. All of this accreditation came through from a joint industry project, which was a project that TWI led that included Lloyd's Register and also 3 TWI member companies, all in collaboration with a view and an interest to certify components. The equipment, as I've touched on briefly, which includes the facility, the powder bed fusion machines, and all primary ancillary equipment were not specified or purchased on the joint industry project. And that's quite an important thing to specify. What we've done here is we've accredited the facility with essentially existing equipment. We have not had the requirement to specify specifics of a machine before we purchased and installed it. So we are taking standardized machines, placing them into our facility, and then having that accredited by Lloyd's Register through several years of research and development. The outcomes from the project, obviously a qualified facility. and processes, and also certified parts that were offered by our end users within the project, and also a certified material. And as David mentioned earlier, that certified material means material that comes from the powder bed fusion machine. And so, yes, this is all very powder bed fusion centric. The guidance notes that David spoke about earlier do contain a number of other AM technologies. And as a continuation of this joint industry project, colleagues within TWI are also working with Lloyd's Register to audit TWI's wire arc AM cell, which contains robotic MIG-MAG equipment. So, but the procedures to facilitate both of these accredited facilities follow very closely to one another, and they obviously link in with the discussion by David. And I just want to run through some of the areas that we focused on specifically to achieve that accreditation. So, what does our facility qualification actually mean? Well, so what we can do within TWI is we conform with the following. We can conform with data development and control, reception, storage and handling of powder, powder bed process and build control, and then mechanical and metallurgical assessment of the formed material. And again, it very much follows the process flow of the previous presentation, and I will dig into some of the more detail of some of these aspects in a couple of slides' time. It's important to highlight that it incorporates our EOS M290 machine. You saw the image on the previous slide of several powder bed machines in our facility, but this qualification is only centered around the EOS, and also it is centered around stainless steel 316L. The reason for that is because to achieve this accreditation, we've had to go through lots of parameter development, lots of procedures, lots of work instructions development, and so this was singled down to a single system and a single material. But what that means now that we've gone through 3.5 years of development to achieve this, it now puts us in a strong position where we can offer to industry developments and uptake of different machines and different materials, all part of the facility qualification. Obviously, if we venture into new materials, into new machines, then we have to be requalified by Lloyd's Register. But because we've now got lots of the procedures and practices in place, we can do this much more efficiently than the process that this took in the first implementation through the joint industry project. So what this now allows us to do, sometimes separately, sometimes in combination with Lloyd's Register as a collaboration, we can now run facility audits, pre-audits, and also offer part certification to industry through our facility. So before I dig into a little bit more detail, there's often some misunderstandings between qualification and certification. So I just wanted to clarify those as best I can. So to understand the differences between the two, we first need to understand what the difference is between verification and validation. So in very simple terms, verification is a consideration: are all things, or are all the right things in there? And the validation is: are all the things in there correct? So what does that mean in reality? Well, let's take the example of, let's say, an Excel spreadsheet. So verification would involve checking that all the required formulas in that spreadsheet were entered correctly in order to calculate the required outputs. Validation would involve checking that all those values were correctly calculated, usually by specific test cases, so i.e. through testing. So qualification is confirmation that verification has been completed and found to be acceptable, and certification is confirmation that the validation has been completed and found to be acceptable. So in terms of additive manufacturing, a qualified facility is a facility that has been verified as having all the necessary equipment, the people, the processes, i.e. the work instructions, the procedures, all in place that will enable you to produce the outputs that have been qualified, that has been qualified for. Certified materials and parts are the outputs from a qualified facility that have been validated and tested to satisfy those requirements of a specification. Now that specification could be regulation, it could be codes, standards, it could be requirements from the client. So in summary, qualification is possible without certification, but certification is not possible without qualification. So in terms of what we did to achieve this, the slide here shows an outline flow chart of the test plan. And again, there's a lot of repetition here with the discussions that David Hardacre is summarised in the previous presentation. So you can see that we have a manufacturing plan in a facility plan that's put into place. And as part of that, we go through lots of stages with the client. So initially, it's the capturing of the customer requirements. So that could be the design, appraisal, file conversions, including powder procurement and characterization, parameter determination, build layouts preparation. So there's a lot of front-end development and discussion that needs to take place with the client. We then implement a root card system that then effectively follows the build all the way through its manufacturing cycle. So this would then include the build on the powder bed machine itself, any hipping trials, or any hipping I should say, removal from the base plate, heat treatments, machining, inspection and testing. And there's no reason why some of this activity, and indeed some of it, was implemented by third-party contractors, where the root card would have tear-offs that would follow the component around. The image that you see on the centre of the slide gives a typical idea of a reference build plate that we used, which contains lots of test specimens that are built around the component. Obviously, for confidentiality reasons, I cannot divulge or discuss the details of the actual components that were built within the joint industry project, but they would ordinarily be centralised in that build plate, and then all of the testing parts would be positioned around it, and some of those would be broken off as we move through the manufacturing cycle between hipping, removals, heat treatments. So we have a record of material properties at every stage of that manufacturing plan. So, sorry, let me just backtrack slightly. So because time is limited, I'm just going to quickly look at two aspects on this plan, one being the powder characterization plan and one being the actual SLM builds. So in terms of powder sourcing and sampling, we, as I said, discussed previously, the powder specification was 316L. We contacted multiple potential vendors and 3 offered to supply. In terms of the development route here, we initially ordered 50 kilograms of the material for the R&D activity. From that, we took 200-gram samples, which were removed from each bottle and sent for analysis. Production quantities were 200 kilograms, and again, we sampled those from 7 bottles, selected randomly, combined and sent for analysis as part of the ASTM recommendations. There are also different recycling methodologies which are also included in the facility qualification or accreditation. There are 2 options that are available. There's single powder charge top-up with virgin material, but obviously this sometimes runs the risk of mixing powders with different histories, and chemical analysis only represents an average of those particles. The other option, in the preferred option for us, was to perform SLM runs until all of the powder passed through once, then recombine the powder and repeat. So this has enabled us to monitor the powders and have the same history of the entire batch. And chemical analysis is also more representative of all the particles in the process. Production powder sampling plan. So before manufacturing, we sieve the powders to less than 63 microns after every use, and again another powder sample was taken. We also then reanalyze the powders to complete the recertification of that powder for every third recycle. Chemical analysis from the powder bed builds were analysed for comparison. So that was some of the activities that were involved in just maintaining a quality control of the powder through the lab and through the facility. In terms of chemical composition, I'm not going to go through all of these. Those of you that are familiar will be able to identify with the processes that we use here for characterization. I think it's quite important to highlight here, though, but we did use subcontractors. Of course, this was all acceptable as part of the accreditation. And then in terms of process parameter development, again, we looked at a number of process parameters based on the geometry of the end use applications, and also taking into account that the material in question was stainless steel 316L. David mentioned in his slides that we could either use manufacturers' recommended processing conditions or we could develop our own. And we took the second line of activity, so we proceeded to develop our own parameters, and alongside that we also developed our own procedure to develop those parameters. And again, those very familiar with powder bed processing, we tend to start all of this by building lots of small blocks in a large test array to understand how the density of those cubes vary with different laser speeds, laser powers across a range of different energy densities, so that we can map out areas where the density of the required deposits are acceptable within the agreed limits with the client. As a second step, we can then use that energy density range, but then start to vary the laser power combinations, laser power and speed combinations, to again determine material density and standard deviation, which again indicates variation in porosity size. So this was a very quick way for us to get to good material properties that were in line with the requirements of the components. And again, as David mentioned earlier, it's important to note that different layer thicknesses would require different energies per unit volume, and different geometries, i.e. thin walls versus bulk material, may also require different parameters. So the parameters that we selected would be suitable for a particular application, a typical geometry range, and not necessarily suitable for different geometries or different applications, and also different materials. So using that process, we were able to develop parameter sets for 316L processing in EOS M290. You will see that we achieved good material density in both the XY and the XZ planes. And what's critical here is that we were able to establish a consistency with this that was suitable for our facility accreditation. So here we've developed the procedures to be able to certify the material, i.e. the processed powder in the EOS system. So I appreciate it was a very short overview, but in summary, why has TWI ventured down this route? Well, we believe that there are some strong benefits for achieving facility qualification and also part certification. And those benefits include certified parts that can meet industrial requirements and approvals, improved knowledge of AM processes and practices, and also it can decrease the cost of certification when using a qualified facility. So thank you for your time. That concludes my short presentation on the work that TWI has specifically done with the powder bed. I think what I'd like to do now is open up the floor to any questions that any of our delegates may have. We've got a panel of several experts that are waiting to answer those questions. So let me look through the Q&A session that we've got open at the moment, and I will try and highlight some of those questions, and we'll see how many we can get through in the next 5 to 10 minutes. So bear with me. So I've got one question here. Which ASTM standard do you recommend in order to compare properties at elevated temperatures and below zero? Is that zero temperatures, such as 200 degrees C?
I can take that one, Carl.
David?
So, I mean, it will depend on your materials and your application. But for example, if you were talking steels, then ASTM A370 provides definitions for different mechanical testing. And then within there, it refers to other specific ASTMs for the different tests. So for example, if you were talking tensile testing, then ASTM E8 would be your default for tensiles ambient. ISO 6892 Part 1 would be the equivalent ISO. ASTM E21 would be used for elevated temperature tensile testing. So ISO 6892 Part 2 is the equivalent for that. And for sub-zero testing, again, it will depend on the material and application, but for example, you might use something like ASTM E1450, which is tensile testing in liquid helium. But ISO 6893 Part 3 will be the equivalent ISO for low temperature tensile testing. Hope that's useful. I can put, I'll type it into the comments as well.
Okay, thank you, David. We have another question here. The system currently planned is self-certification by each manufacturer or third-party certification by TWI?
I probably answer that one as well. So again, I'm sorry to keep saying it depends. It depends on the industry and what you're making. So, for example, if you're making, it's something we haven't covered today, but if you're making aerospace parts, for example, or medical parts, then in those industries, the Tier 1 would write a spec that is audited by the regulator, and then that specification gets flowed down through the supply chain. And different parts of the supply chain, so for aerospace, for example, you might have to meet a NADCAP audit scheme. So in those industries, you wouldn't require a third-party organization because those industries work different. So it's more like a self-certification, but within that regime that I just described. In other industries, like marine or oil and gas, energy and process, then third-party certification is a legal requirement. It is required. So in answer to the question, it does depend on the part you're producing in the industry that it's going into, whether it's self-certification or third-party certification. What I would say, though, is where you are using third-party certification, get your certification authority, whoever that is, involved early. Get them involved right at the start, because you need, as a manufacturer, you will want to understand what your witness points are before you start making anything. To avoid rework. Okay.
Okay, thank you, David. I think there might be another question coming at you now as well. The design engineers require further guidance, in particular selecting the correct standard to apply when it comes to HIP process. Do you recommend ASTM or BS ISO EN standards?
Okay. I don't personally recommend either. As a third party, I'm not allowed to. Otherwise, I would lose my. I wouldn't be independent anymore. So it's up to the manufacturer to choose. But what I would say is it generally depends on, again, the maybe not necessarily the industry that you're working in, but where those parts are going to be marketed. So if you're in North America, for example, and maybe you're working to an ASME standard, maybe the boiler pressure vessel code, something like that, then it's more likely that you'll be using ASTM standards to support that. So if you're working to ASME, then you might do your tensile testing to ASTM E8. Whereas if you're making the valve that I mentioned in Europe, and you're working to either a specific valve standard, or maybe the pressure equipment standard in Europe, so that's EN 13445, then you're more likely to be using an EN or ISO standard in that case. But that doesn't mean to say that you can't use ASTMs. You absolutely can. So which do I recommend? I'm sorry, it's up to the manufacturer. It's the one that best suits your application. But what I would say is, in terms of fulfilling that requirement that I said, that equivalent level, demonstrating an equivalent level of safety, then either ISO or ESTM would do that.
Okay, thank you, David. Question here. The measures required to certify a part clearly create an additional cost for a given part. Have you made an estimate of the cost as a percentage of the manufacturing costs of a given part? What are the main components of this additional cost?
I think I'll field that one. This is Tom Massio. So I imagine this is based on the measurements, meaning mechanical testing and such. So yes, there was additional costs from this and doing that, but that's really to validate it. And with it being a validation process, you might do that with any sort of quality assurance process, and then compile all your information, and then know where you stand as far as mechanical testing. So something that might be used to reduce that cost is putting samples, instead of doing the validation all at the front end. Put samples on each build that you're doing, say in a large-scale production environment, and then do testing every so often. It might start at every 3 to 5, and then go to every 10, but keep those samples spare. Then do testing when needed on those samples. I hope that's a useful answer.
Okay, thank you, Tom. I think it's probably worth adding as well that, well, firstly, we didn't have a specific part of the joint industry project looking at the additional costs because we weren't doing it in a streamlined way because it was a research project, but it's certainly something that can be looked at in a following project. And also, it's also good to take into consideration that there may be some additional testing required during the process or additional samples to be manufactured, but sometimes these can then reduce your post-process inspection further downstream. So you may have to perform less NDT checks if you're going into production. So there's lots of things to think about on that front. It was a good question, and it's probably not clear yet how that can be answered in its entirety. Probably got time for one more question. Although not related to the actual manufacture of AM components, when welding AM produced parts to more conventional produced materials, roll plate, pipes, forgings, etc., is it acceptable to use EN 15614 pre-qualified weld procedures?
It's Adrian here. I'll take that one. The answer is generally yes, because the grade of material that you would be producing by AM would fall within the grade of material for your pre-qualified welding procedures. And in our experience, welding most conventional materials to most AM materials are not problematic. So in general, yes, but I would personally recommend a very small validation of that welding procedure before you go into full production.
Okay, thank you, Adrian. And let's take this last question here. If you use your qualified EOS machine for non-stainless steel material, for example, titanium, would you need to re-qualify in order to go back to stainless steel?
Shall I take that one, David, again?
Yeah.
So, I mean, it depends on the scope. So when I talked about the scope of qualification, it could be if a facility is qualified for multiple materials, so for example stainless steel and titanium, as you just suggested, then when performing that qualification, they would have to perform qualification builds in both materials, because they have to test both materials and demonstrate. The validation activity is demonstrating those the material properties meet the spec requirements in both cases. as well as that, as part of the audit, if the same machine is being used for multiple materials, then there is an additional requirement, into a procedural requirement in terms of material changeover, because of course you've got an additional risk of cross-contamination between different grades, well, different materials. And in fact, with titanium, it goes beyond that as well, because there's a further additional requirement, because it's a reactive material. So there are additional hazards if you're handling titanium and aluminium, for example, which are reactive powders. So all of that is covered in the audit. Now, so that's I think answers the first part of the question. The second is if TWI, for example, had performed a build in stainless steel and then went on to perform a build in titanium, would they need to re-qualify the machine in between those? No, they wouldn't, because they've already qualified for both materials, but they would have to follow their procedure for a material changeover. And within that changeover procedure, it would include, I've got to be careful. I can't go specific unless Tom wants to declare exactly what you do. But they would have to follow that procedure to make sure to show that they were following that procedure that mitigated the risk of cross-contamination. But it wouldn't be a whole new qualification.
Okay, thank you, David. So I think we ran out of time now. So we have a number of additional questions logged. So what we will do is we will go through these questions and put answers to them, and then I guess post them on the website. I'm not quite sure exactly how we do that, but we will certainly get answers to those questions to people sometime in the next week or two. So I think it just leaves me to say thank you for all the attendees for your time over the last hour to listen to the work that's been done by Lloyd's Register and TWI on additive certification. I'd like to thank all the panel members for answering the questions, and also to Stacey, who has been arranging and planning and preparing the WebEx this afternoon. Stacey, is there anything that you need to say as a closing statement?
No, just that we'll circulate the recording and a copy of the slides to all the attendees as well.
Okay, thank you, Stacey. So it just leaves me to say thank you again to everyone, and I hope everyone enjoys the rest of the afternoon or evening, and hopefully we will engage at a point near in the future. Thank you. Bye-bye.